Me doing all the talking, not so much fun, right? So we're gonna have some exercises and warm-ups. First of all, the girl with the pearl earring is kind of glancing that direction. Figure out from that direction, in your section, on your row, are you an odd or an even person? If you might decide that you want to be odd, that's fine, I'm pretty odd. That's okay. If you think you're more even, that's fine too. You don't have to let math dictate whether you're odd or even. Not my thing, all right? Odd or even?
Odd. Even. Should we count from 0 or 1?
You can count from whatever you want. It doesn't really matter to me. All right, you ready? You know whether you're odd or even? Follow the instructions, please. If there's nobody to your right, that's fine. We are experiencing some delay in the network. Well, a lot of delay in the network, actually. More delay than I expected in the network. Oh, there's a little bit of some transactions moving. Not many. Marshall's in an island.
You can call me Nomad.
Yeah, maybe this is a bad early morning thing to do, actually. I'm starting to... No?
Is this what a CPU feels like?
I don't know.
There's more instructions. Okay. What's your idea?
Oh, your instruction for the odd and even are at the bottom. Your top instruction is for everybody. Yeah. We have some numbers flying. I hear no colors. It's interesting.
Chartreuse.
Oh, chartreuse. Good. Nice. Very good. Of course. The opposite of whatever you want it to be. Yeah, the opposite of chartreuse. Anybody have an opinion of the opposite of chartreuse? Scarlet. All right, we have an answer. Scarlet is the opposite of chartreuse. Who would have known? There's real math going on in the front. I want you to know. The bus system in the back is very slow. We've got relatively fast clocks up here in comparison to in the back.
Respond to the left? Yeah,
you respond to the person who told you, do you not?
Yeah.
That's the response. That's the idea of a response. So you get an answer, and then the response is to where...
No, it said, oh.
And you keep going.
Wait, he said respond to the person.
Are we doing it? Oh, we've got some. Yeah, I think we've got some packets dropped. We're going to just move on. But we now have some favorite colors. We know what your favorite number is. We're pretty much getting ready to crack your bank any moment now. This is going to be great. All right, so hold on to that for a little bit. So I do work at Intel. I work inside of a group that deals with power management of the device. If you think about a CPU, most of us think about the cores of the CPU. It might have some functionality, some different peripherals or things that are on that device. And what we normally don't know or think about a lot is that way down inside, deep down at the bottom, there are a whole bunch of microcontrollers doing a whole lot of work to keep things going for you. And I work in a group that does that, deals with both active and not active power management, bringing things up, making sure that your YouTube video plays for a while. There are a lot of things going on inside of your CPU. There are a lot of devices, there are a lot of peripherals. And as a result, there's a lot of stuff to coordinate and things happening. And things happening, and lots of them, and happening whenever they want, is sometimes kind of a pain and error prone. And it creates a variety of different problems that we have to solve. I want to talk about some of those this morning, and I want to talk about them in relation to senders and receivers and how that will actually, I hope, help us. All right, we are going to, or I am going to be using this development board for our talk this morning. Why this development board, you ask? Why did you pick this one? I picked this one because in 2019, I bought a big big box full of these, and motors and motor controllers. And I had in my mind, I'm going to, at CppCon, do an embedded class. We're going to build robots in 2020. Yeah, that was not maybe the best plan. I mean, it was a great plan until 2020 occurred. But then I suddenly had this thing where I had a box full of ARM processors, which was sad because I wasn't giving a class, but then I was very popular because I had a box full of ARM processors, something you couldn't get hold of. It was like gold. But then I found out I didn't have the ARM processor that anybody wanted. So anyhow, long story short, we're going to use this little board. So let's take a look at what this is. The basic inside, we'll just look at the top level of the bus. We have a variety of different things, but we have a core, and the core is just an 80 megahertz core. It has an FPU on it. Let's see if we can get the right pointer here. All right, and it has some flash, 256K of flash, and a cache. The cache is there for being able to do prefetch for instructions out of the flash. It has memory. You'll notice 64K, but unfortunately divided up into 2 segments. So we have a little bit of RAM. We've got a core, and some other bits and pieces. So up here, this quad SPI memory, this is the type of thing that you would hook up your flash memory to if you had like a flash drive interface. DMA is very nice. So DMA is like a little engine. This little engine, you can program it to do a variety of different things for you. For example, I would like to send some data out through some port, and it's all queued up in this memory segment, and I don't really want to take care of constantly servicing the I/O. So you can program the engine to service the I/O. When the output buffers are empty, it can go ahead and load up the next segment, or on the input. So DMA, we've got a couple of those. We've got this touch sensing, so this is CppSense. There's 3 of those. There's some general purpose I/O. They can become interrupts or other things along the way. Anything else? Oh, there was a random number generator. That's cool. So there's a random number generator up here. There are a variety of different buses that run through. AHB is a standard, an open standard from ARM. We have timers. You'll see these TIMs all over the place. So there's a bunch of different timers. Here's a SPI. Some universal asynchronous transmitters, so for doing serial communication. I2C, here's a CAN bus. Kind of getting the idea, there's a lot of different junk, some comparators. Here if you wanted to do serial audio, a digital analog converters, low power timers, so they work a little bit differently, and even an op amp. So there are lots of different peripherals within inside of this little bitty device. Just so you don't get the idea that timer just means a little timer where you start counting some things, here is the simple version of the block diagram for the timer. The timer has a whole lot of comparators. It has a bunch of different types of ways to take input. You can do edge detection, so you can start based upon a signal coming in, start timing, stop timing based upon other signals. If you wanted to do PWM comparisons, you can start doing PWM. You can set up the counter so that they can interplay with one another. All of this so that the CPU, or the little microcontroller, doesn't have to do any work. It sets something up, and these things just run along. They do all the work along the way. You may notice there's a variety of these little squigglies that kind of point upwards versus the ones that are pointing downwards. The squigglies that point upwards are all places where we can have interrupts that the system might generate, or events. So there are a lot of little squigglies on this particular timer. In fact, there are a lot of little squigglies all over this device. So there is an opportunity to be alerted or interrupted along the way a lot. So let's talk about interrupts. So if we have something very simple, we've got one little core, 2 timers, a DMA engine that's servicing an I2C device. We have maybe some amount of work that we want to perform. One way of doing that is we can poll. right? We can simply just keep checking. Is my timer value what it should be? How about this timer? Is it what it should be? Am I done sending information out the I2C? Have I gotten something in on the bus? Go back through that cycle again. Keep going through that cycle again. Keep going through that. You get the idea. As we keep going through the cycle, though, there are inefficiencies in polling. Did we poll at the right frequency for the thing that we're trying to find? Maybe we don't want to actually just consume power all day long. Maybe we want to sleep for a little while. Did we sleep too long? Did we miss some events along the way? So going through and looping over events and trying to figure out what the right timing is for some particular event and how we want to loop, not necessarily the best way to do this. And so therefore we have interrupts. Interrupts allow the core to be woken up and told that something important is going on. And those can be generated internally by some of these devices, or they can come externally from the device and brought in to wake you up, or to tell you that something's going on. The peripherals for this little bitty device, 24 GPIO, 14 different communication interfaces, 11 timers, because you can never have more timers, an ADC, a DAC. There's a lot of devices that could be creating interrupts and asking for requests of things to do. It'd be very inefficient to go ahead and scroll through each of those, iterate through each of those, and try to figure out what you have going on. So let's talk about what an interrupt is. So as we are processing instructions, different instructions may take different amounts of time. And depending upon the instruction, there might be a different number of cycles that are required to perform that. And an interrupt is nothing more we can think of as a signal that occurs to the core. And when this signal occurs, it can occur anywhere along the way. And it's the processor's job, it takes care of this for us, to handle what happens with that particular instruction that's in flight when the interrupt occurs. There are generally three things that happen. One is the instruction will complete. It's not going to take much longer. It will complete, and then the interrupt will be serviced. The next thing that can be happening is, for example, in this particular device, if you're in the middle of doing a divide, division takes a long time, and that will be scrapped, and the processor will remember that we got to come back and start that all over again the next time that we resume back to where we were. The other possibility is that you're in the middle of a long load or store, and we go ahead and suspend that operation and come back to it later. So when the interrupt occurs, what we want to think about is, at this point, it's as if somebody grabbed the processor and said, yeah, whatever you're doing, stop when you are done with this instruction. And we are in this now transition phase. During the transition, this particular processor will go ahead and push all of the bits and pieces on the stack that it needs automatically for us. It will go and grab from the interrupt vector table that's associated with the interrupt that's going on, what is the address that I need to jump to, and it will begin executing at that address. When we're done at the end, it's the opposite. Right? We need to restore the things that we push so that we actually have a stack that's available again, and the processor will take care of that for us, and then we just continue on our merry way. So this is basically what the interrupt is going to perform. Okay, interrupts are controlled by these tables, allow us to decide a couple different things about interrupts. One, there are different types of interrupts that are built in, and those are fixed. They actually have these negative priority numbers. Unfortunately, there's not a -0, because that would have been cool, but there's not. So the negative priority numbers are system exceptions. They're events that the system's going to handle. They're very high priority. How priorities work are the lower the number, the higher the priority. They are fixed to some acronym or some description. These are all assigned somewhere. This particular device has 63 interrupt locations. And when an interrupt occurs, the address here is the address that contains the interrupt vector. So It's going to go and pick up where to jump to and where to start running from. You'll notice 0 is reserved for this one. 0 is where the initial stack pointer is going to be. So that's where your stack is as this thing boots up. It's stored in that address. And there are, in addition to, this is just unfortunately confusing, in addition to this thing called priority here, which is the interrupt number basically, there's this priority type. We can change the priority. This device has 16 priorities, which means that we could control the priority of an interrupt. So priority of an interrupt of 3 goes off, and then later one of 0 goes off. 0 is a higher priority than 3. It will take over that. This is the in part of that invic. It's nested, and it allows us to actually have interrupts within our interrupt. Okay, where are we going with all this? So we have a interrupt. First of all, we're running along on our main, and we have a priority 4 interrupt that occurs. So this is our little transition, right? It's going to take 12 cycles. These 12 cycles are used to go ahead and store off our registers, find where we need to jump to, and jump. Okay, that took 12 cycles. Meanwhile, we're executing on priority 4, and priority 0 interrupt occurs, and we've got to do that again. We're in the middle of executing something, so we go ahead, do those same 12 cycles, we can begin executing. Once we're done, there are 12 cycles for this to restore, and we come back and we continue on our operation. Now, while we were in the middle of priority 4, or really actually any time that we started here, another interrupt of priority 4 could have come in and actually held itself in position. So it is pending. It can't run because there's already a priority 4 interrupt running. But there's this thing where we can do tail chaining, and instead of actually taking these 12 cycles, it only takes 6 cycles to figure out where to jump to and what to run next. All right, phew, we got all that figured out? Perfect. Yes, question?
The priority 0 could happen in the transition state?
Can try, yes, great question. So if we were actually in this transition state, could priority 0 occur and take over? Yes, it can. Yeah, so this device has a late lookup in order to make that determination very last moment.
How does it remember what interrupts are in a queue? Is there a queue? How big is it?
No, the queue is a queue of 1. So there are 2 parts of this. The interrupt has the priority level of the interrupt, the one that we assign to it, how important we think it is. And it has its number, that 1 through 63. And between those 2 numbers, you can figure out which priority is going to be set, or excuse me, which one is going to take precedence. So first, it's the priority of the interrupt, the lowest number. There might be collisions of that. And then it is the lowest number of the actual interrupt assignment along the way. And so it's just a bit vector, right? We just store bits, and they're just hardware. It's awesome.
Can you miss an interrupt?
Can you miss an interrupt? You cannot miss interrupts. Yeah, the interrupts are latched internally. I mean, it depends on what you mean by missed an interrupt.
Like while a 4 is happening and a 3 comes in?
While a 4 is happening and a 3 comes in, no.
Or a 5 comes in?
Yeah, so what will happen is, let's say we could just think about them as external interrupts at the moment. That line either goes high or low or whatever it does. The CPU, or in this case, it's the logic internally is sampling that signal. It has some sample amount, or some sample, frequency. And it's either edge detected or it's level detected. There's a whole bunch of different rules about the interrupts that we probably won't talk about at the moment.
One thing also to note is it's the responsibility of the code that's handling an interrupt to clear the interrupt.
Yes. So there are different types of interrupts. Some interrupts will clear themselves. Once that hardware has been satisfied, you've read the buffer, it's now gone empty, it will clear the interrupt. Or maybe it interrupted because it was empty and you've now filled it back up, it clears itself. Other interrupts you have to clear. There are level and edge detection. So edge detection is like the event occurred, until it occurs again, I don't care. Level is it's active and it's still active. And so unless you clear it, it's still an active interrupt. All right, so basic idea of interrupts.
Yeah, the question that was kind of floating by there, if a
priority 5 interrupt comes in, and there's just a lot of stuff going on.
Yeah.
When does it ever happen?
Oh, if there's a priority of 5 and there's a whole lot of stuff happening, like if you have higher level interrupts, it may never happen, right? Yeah.
Ends up missing an interrupt.
Yeah, so missing, eventually, you hope that you don't have so many high level priorities that you get to your lower ones.
The priority 5 came right when priority 4 started. It happens at the end.
Yes, it happens at the end. Lower priorities always will happen at the end.
So, just to address the question, it can happen that priority 5, for example, is a mutex, right? And priority 1 wants to have a mutex. Then we have to do some sort of priority inversion, but this is to be programmed in the software, right?
So you use the word mutex? I have no idea. I don't have those. It's one of the M words that we won't say today. Yeah, so we will talk about shared resources and priority inversion here in a moment. Yeah. All right. So there are 2 basic rules that we're going to use. One is you want to return from your interrupt service routine, that routine that's handling the interrupt as quickly as possible so we don't end up with problems. In essence, we don't want to do work inside of our service routines. We want to capture some state and pass then that work off to be done elsewhere so we don't end up with issues. So how are we going to work with our interrupt service routines? Well, there are a couple different ways. One, we can work with interrupt service routines simply by saying all the work is going to happen inside of the service routine, the thing I just said not to do. But sometimes it's really simple stuff. Like you're servicing the fact that a buffer is now empty and you need to give it some more data. You're going to do the memory read, you're going to shove it inside of this register, and you're done, right? So sometimes interrupts and what we're doing very fast, we're going to take care of something very quickly. Other times, not so fast. But if it's contained within the ISR, we can do our work. This is really nice, right? These things have no coupling. They're just like they're going to do their work and we're done. Wouldn't that be nice if all of our code was that way, by the way? It'd be awesome.
Is there any information that comes with an interrupt, or is it literally you just jump somewhere?
Oh, it just jumps somewhere, and then you do whatever you want to do. Yeah, there's no information that comes with the interrupt, so to speak. The interrupt is a signal, and you are suddenly running at a pointer somewhere else, right? You're running code somewhere else. It's like a function got called. And so when that function got called, you're like, oh, well, this function got called because this particular interrupt went off, like my audio buffer is empty. Yeah, that's a high priority one, right? My serial audio buffer is empty and I need to get more data to the serial audio hardware so that it can do the next thing. So there might be a bunch of registers that you read in order to do that along the way.
But so you know which device sent it necessarily, or could it be multiple devices send it? Do you have to check all of them?
No, there's no sending. It's just like that's the function that got called, and that function is related to that interrupt. So those 63 interrupt vectors will have 63 functions, or usually different functions. Sometimes the same functions, however you want to do it. Sometimes though we have work to do, right? Okay, and so when we have work to do, we have to have something a little more complicated, a little more advanced. In our ISR, in our interrupt service routine, this function that gets called, we're going to go ahead and grab some state information or something to do, and we will shove it inside of a work queue. Or we'll set some flags. And inside of our main loop, then we're just polling the next thing to do. All right, so this is another technique. And this can work, but there's now suddenly a bunch of information that might be getting shared along the way. Things can start getting a little more complex. When things start getting more complex, like for example here, going back to this, if we shove something in the queue and we're pulling it out and dealing with it in our main loop, for example, a message came in, I want to do something with that message. Now, this interrupt down here occurred, and this interrupt basically says, hey, I'm really hot. In fact, I'm almost on fire. Do something now. I'll get to it. I'm busy servicing this message over here that's asking me some, really cool question like, what is my battery life or something? I don't know. That would be bad, right? And so we want to be able to say, this thing that just occurred in my system is really high priority. This main loop here may not be able to handle that for me. One thing that people will do is they'll start making the atoms that go inside of the queue smaller and smaller, right? So you're doing less work. But now you're breaking your work tasks up to be really small. Eventually, you decide that you want something that allows you to prioritize what's going on. And this prioritize what's going on, we can actually create software interrupts. So just the same way that hardware creates an interrupt, we can just take control of the hardware and let software create an interrupt. And now, suddenly we have ways to switch tasks. So we have high priority interrupts that can occur, and we've got lower priority, or we can think of it as high priority queues and low priority queues. And so as long as there's something in the high priority queue, we'll continue operating on that. Otherwise, we'll look on the low priority queue. So imagine some piece of hardware out here doing something interesting, looking at some messaging bus, taking that information in, figuring out what in the world's going on, putting it into something that looks like memory that we can access, and then says, hey, I got a message. Do something about it. And doing something about it pulls an interrupt. We grab this information and we decode it, and you're like, yes, but Michael, you said the rule was not to, and that's like a guideline. So we're gonna do some work. We're gonna decode right here what in the world the messages that came in, and you wanna know how we do this really, really, really fast so that it can fit in the ISR. You'll go to Luke's talk later today, and we'll talk about how we make messaging super fast. So this decode then, we can, based upon the message that came in, decide, is this something that's, belongs here? Or does it maybe belong down here? And the main loop is just covering this one. By the way, we just call this quick as a bunny execution, right? Okay. Or maybe we got a second one here. And meanwhile now, our mechanism, we have a scheduler basically that's handling, based upon interrupts, handling the different work that has to get done. What do we do when there's no work in the queues? Yeah, like real sleep, right? Like power gate things, like shut it off, like stop wasting the battery. So now we have a technique to actually say that I don't want to waste battery anymore. I want to start shutting things off. All right, this is all great. When there's no more work, there's no more twist. When there's no more twist, the mice go home and they sleep, all right? So what's the problem with all this? It seems great, right? Should just work. Okay, here's the problem with this. So, soon chronos is the ancient Greek for synchronous, where we get eventually from the Latin, meaning with time, with time. Asynchronous, as soon as you put the A in front of it, it means without time. You all were doing okay. Well, some of you weren't doing anything, to be quite honest, during our little exercise. But some of you were doing okay. And then I noticed there were a few of you who were getting responses while you were trying to talk to somebody else, and you suddenly had to turn the other way, and you kind of were like trying to figure out what in the world was going on. Asynchronous things means without time. It's not in your normal mode of operation in which you have been servicing things and suddenly, oh, hey, did you want something? Interrupt-driven events are completely asynchronous. Down under the hood, eventually things are just asynchronous. A lot of the things that we work on are event-driven and asynchronous. Parallelism. For us, parallelism comes from hardware. The beauty of my job is I get to make decisions about should this actually go in silicon or should this go in actually firmware? Do we make an accelerator that makes this thing do what I need it to do better? Or do I have to actually, for some reason it needs more manipulation or changes over time and therefore it should actually be in firmware? But these little hardware devices are constantly doing work. They're doing things on their own, and there's parallelism all over the place, even though there's only one core. You were just experiencing this, those of you who participated. You gave some of your information off, somebody did some processing on it, and then they gave you an answer again later. That was being done, I don't know, by some little engine that could add or subtract next to you or tell you what the opposite of a color was. So everybody seems to have a different idea of what concurrency is. This is my idea of concurrency. Concurrency is really, when I think about concurrency and the problem associated with concurrency, it's a problem that deals with independent execution and pulling that back together with the state that it belongs to. If we had independent execution and we never needed to worry about state, we wouldn't have concurrency issues. The reason we have concurrency issues is because we have independent execution. We can think about problems independently. They can be divided up, may or may not happen in parallel, it doesn't matter. We can divide up our problems, but we have to associate the execution of something back with common state again. And this creates problems, constant problems. So let's do a simple one. We have a proxy. It gets asynchronously asked a question from agent 1. It knows part of the answer, it doesn't know all the information, it has to go off and ask agent 2 some information. Agent 2 receives something, but maybe it doesn't really actually have a get an answer, provide a response. It deals with life as, oh, you want this particular thing? Yeah, I'll broadcast it out the next time I'm around. So it broadcasts some things out a little bit later. Now, meanwhile, we get this information back. We now need to respond back to agent 1 with what's going on. These are asynchronous actions that occurred. And when they're asynchronous, it means that I need to somehow, this thing that came in has to be associated with the original state so that I know where to respond. I might need to know part of calculations that have occurred. I need to put these things back together. And this is pretty simple with one thing, but now what happens if I have 10 of them going on simultaneously? Or maybe 100, or maybe 1,000? And I'm constantly getting told and woken up and try to figure out, I'm getting parts of calculations simultaneously, but I got to figure out how to take the bits and pieces that I have and associate them back to the state that I'm in the middle of so that I can figure out how to get the right next answer back out. And that is the problem. Wouldn't life be great if we could just spin weight for everything? Yeah, I'm sitting here at priority 5. I asked for a response and a question. I'll just spin because I know that's going to happen at priority 0. I'll wait till it's, got my answer. Something will take and change some atomic flag. When that changes, I can go on and keep processing again. Well, that's great from a mental point of view because we actually entered into a spin. All my state is sitting on the stack. I know where it is. I don't have to do anything. I just can continue executing again. But life becomes hard when I can't spin because of maybe priority inversions that are going on. Part of the answers I need are actually going to happen and this thing's going to run on priority 6. I'm spinning on priority 5. Will I ever run on priority 6? No, it'll never run. There are all kinds of problems that occur, including just burning power. So spin weights are awful. And so this is a problem of I have events and I have state, and I've got to somehow put them back together again. This is not a new problem, but this is a problem that a lot of people have been thinking about for a long time and trying to figure out how do we solve this? How do we solve these events that are occurring, this asynchronous type activity? How do I pull that back in together and associate it with the actual state? So, bringing the state to the event. An event occurred, I grab some shared state, I pull that in, and I work on it. How does this work out for you?
Badly.
Yeah, badly, almost every time, right? Shared state almost always works out badly. We stomp on things that we don't mean to. We were like in the middle of data updates and we tear the data. Okay, well, let's just make it atomic. Well, what I really meant is the whole entire cluster is atomic, not just that one thing's atomic, but I don't have mutexes. I have to what am I going to do, right? So bringing the state to the event execution and trying to solve it that way, rife with problems, really hard to do and get right. Back in the early 90s, I was introduced to something called ROOM, real-time object-oriented modeling. It used an idea of actors. It was very popular in telecom. We used it in semiconductor manufacturing equipment dealing with robots and lots of other things. The idea is that you bring actually instead the events to the state. You do that through messaging. Actor models is a way to help try to solve this problem. As events are occurring in your system, you route the events to the state, and then the state goes ahead and takes care of it, and they're all right there in one spot, and you're not creating problems for yourself. But at the end of the day, most of your state machines end up looking like this. Just some sequential computation, or I've got this, I'm in this state, there's only one more state to move to, it's this one. There's only another, and you just keep sequentially moving along in your communication process or in what you're trying to accomplish. Everything is like, do this, then do this, then do this. There are exceptions, but a lot of it looks like this. And then you have, of course, two things. You have the cancel in the hierarchical state, and you have an error. So we can handle errors and cancellation at the top. So back in 2014, I saw somebody give a talk who had been thinking about this exact same problem. And as I sat there and I had been playing with actors and kind of not entirely excited about them still, many years later, trying to think of another way to handle this, I'm like, Kirk, that is a really incredible talk. It ends up, Kirk was talking about asynchronous sequences and how to put them together with data. He was really interested in algorithms. And part of the problem with that previous diagram is you start to realize that you have certain algorithms that you just want to reuse over again. Well, you can't. It's really hard. How do I apply these same techniques over and over again? It's hard in the state machine. It's hard to do. Eric, a couple weeks ago, said, hey, I get a lot of the press for senders, but really, it's the brainchild of Kirk. Kirk has been working on this problem for a long, long time. This idea of how in the world do I take asynchronous things and apply either algorithms to them? How do I treat them in a way that I can actually think about these things that are asynchronously occurring in some structural way? So, senders. This is the diagram that a lot of you maybe have seen of senders. It has a couple different things in it. We're not going to care. Because I want to come at senders a little bit differently than we normally have, or at least a lot of the documentation has. A lot of the documentation talks about senders from the bottom up and how in the world these bits and pieces of the design of senders work together. I want to talk about, as a user, how in the world do we use senders? What do we do with senders? And the one thing I'll just mention is this here, this operation state at the bottom. This is important. The state is going to be part of this thing along the way. It's bundled up. Okay, so let's step back as a user. There are three parts as a user that we need to deal with and worry about. There are sender factories, sender adapters, and sender consumers. Notice what word I didn't say, by the way. There's no receivers. In fact, we're going to start seeing over and over again sender factories, sender adapters, senders. We're going to talk a lot about senders because we're users of this thing. Sender factories are functions that return senders. They don't start off with a sender. Generally, they just return a sender. They have a sender, like you get a sender out of them somehow. There are a few. We will be using the items that we're going to be using are all out of a library that I'll reference here in a moment. So these are sender factories, just result of, just error result of, just stopped are some. Just is kind of like what it sounds like. It is going to take some values, and it will be a sender that will produce those values when it's time for it to run. When it does its work, when it does its thing, it will produce those values. So in this case, it's going to produce 42 and 17. Just result of, so the just result of version is when it goes and executes, when it does its thing, it's going to run some functions. And whatever those functions result in, that is what it will produce to the next stage. Okay? So we've got then just and just result of, and if we think about it, okay, just and just result of are dealing with values. And then just error and just error result of are going to be the equivalents, but they're dealing with errors. So they're going to produce just errors. And then just stop is going to produce the stop token. So that's interesting. Those are the three parts that I had in my state machine that I also worried about all the time back in the day. Values. It's the part that we're really good at, by the way, right? We think about values all the day. The thing that's like the important part, whatever the task is that we're trying to perform. Yeah, I'm going to get this message in. I'm going to pass this message over here. It's going to do this work. And then after I get that work done, I'm going to go over here and I'm going to do this other work. For us, maybe, we've asked for some information and then we get some information. Most people, when they think about reading registers, reading memory, it just happens. For us, it could actually fail. I mean, how often, like when you decide that I want to just read a register, that read might fail, right? You might get an error back. Well, we got to deal with that error. And suddenly you realize, I didn't just get my value back, I got an error. Oh, okay, well now I got to rework my code to kind of like shim in that error. Don't look at me like you've never done this before. Right? Eventually you're like, okay, all right. Those are errors too. And then somewhere along the way you realize, well, not only do I need to deal with errors, but actually controlling the power management of that thing, and I just shut its bus fabric down, and I'm never going to get a response. I might have to actually cancel that transaction that I'm waiting for because there's not going to be a response. I just shut the power off. So cancellation then is the next thing that you come around to, and you come around sometimes late in your project of trying to figure that out. And how many of you have like a comment in your code that says, we should figure out how to cancel this at some point, but it's hard? Okay, so some of you tell the truth and some of you are liars, but it's okay. We now know. Not anymore, all right? So it's been solved. Good. Yeah, cancellation's hard. And cancellation can't be thought about later. It has to be thought about at the beginning in order to get it done properly. And so right away we start seeing from the sender factories some of the advantage or what we have inside of the sender design. We have values, we have errors, and we're going to have the ability to do cancellation. Really, those are the key things that I always need. They're the problems I've been trying to solve since 1990. It's like this constant problem always. And it's always thought about like, how do we get this in later? Well, it's like in the design at the beginning. Okay. We also have another function that we're going to think is important that returns a sender, and it's schedule. And schedule is going to do nothing more than provide us a place at some point where we can actually do some work. All right? So now, senders are lazy, so they haven't done anything. We just have a sender. It represents something. Now, sender adapters is where it's at. I mean, if you wanted to grow up to be something, you wanted to be a sender adapter. Sender adapters are the algorithms. They're the things that allow us to piece and put together all these different types of asynchronous bits and pieces that we think about. And we can start to see what some of them look like. Continue on. Continue on's nice. I've been doing some work, and now I want to continue on in another scheduled context. For us, an example would be, I just received an interrupt. It was a high priority interrupt. It was like in fact, it was the highest priority interrupt. And I realize now I don't really need to do this thing right this moment. I need to do it later. And when we think about priorities and interrupts in our context, those priorities represent how fast or how soon do I need the answer to come back. It's very close to like deadline monotonic scheduling. So the idea is that I need to produce a response within a certain amount of time. Well, how fast do I need to produce this response? Quick as a bunny, nobody really cares. It's in a few milliseconds. Stick it at the bottom. I need the answer now. It's got to come out in a couple nanoseconds. That better go up a little higher because I need an answer in a couple nanoseconds. This one needs to come out in somewhere like in between. This is a few microseconds. Goes inside the few microsecond bucket. And so as we start thinking about where do we put things, hey, I now know what I need to do, but I don't really need the answer now. Let's continue this on somewhere else. We'll start seeing some of these a little bit later. The let value, let error, let stopped. Hey, that sounds familiar. Again. Then do this thing, then do this other thing. Sequence. Sometimes you just need this thing and then the next thing, but you don't really need the state in between them. They just need to be sequenced one after another. What do I do when I have an error or when I've been asked to stop? We have some additional ones, repeats, retries and until, split out, and then when any and when all. So these are starting to look a lot like some algorithms that we might recognize. And then on the other side, then we have consumers, things that take a sender, but they don't produce senders, they just consume senders. And really, these are the things that are going to start the work. Once you decide that you want to consume a sender, then now you can start all of that work that you're going to do. So we have 3 versions of this: start detached, unstoppable, we're never going to stop it, and sync wait. We need to wait until the operation is complete before we can move on. So really, I think we should have rebranded this. Employing senders to tame concurrency in embedded systems. We don't really talk about the receiver side of senders and receivers, not as users. The receiver side is going to be what we attach to. It's going to receive the response, but we don't really care at the moment. So values, errors, and cancellation. These are the main parts of our interface of the design. And we're able now to take and deal with value channels, error channels, and cancellation. All right, composition. So I love, and you probably already know this if you've ever seen any of my other talks, I love declarative systems. It reduces the number of errors that I have. It allows me to think and localize ideas and concepts and put them all in one spot. Hopefully it lets me do a lot of checking at compile time that the construction is correct. In senders, we have composition. So we're going to, on S1, we're going to schedule something. Get the right pointer up here. We're going to schedule something, then do something else, then continue on a different scheduler, and then take that value and return it as a string. Now, this here represents something that I want to do. It is this chain of senders that I've put together. I've composed them as something, but it doesn't do any work yet. Now, if I go ahead and pipe that off to sync wait, this is now the consumer of the sender, and now some work's going to have to happen. Well, what is the work? I already described what the work needs to look like. It's going to schedule on whatever S1 was. It's going to then simply return 42. Then it's going to move over to this other scheduler, do a toString, and return the result. Now, if we want to get that value out somehow of this chain, the result here is actually an optional of a tuple. An optional if it has a value. Tuple could have multiple return values. And we can get our string back out. So That's what composition looks like. Yes, we'll see a lot more of this. But
What happened to the 42?
it was converted to a string.
Did S2 receive it?
Got it, okay.
Okay, so through the magic here, I guess I should have spent a moment on. Thank you for asking. On S1, we simply produced the 42. On whatever that schedule thing is, we produced the 42. Somehow that state has been captured and it's going along through the value channel. And as a user, I don't really care. I mean, I might care, but I don't care at the moment. And then on S2, the 42 now, that value has been passed into this, this callable will be the argument. And then toString is called on the 42, and then the final result is yanked out when we actually run it.
Why does it continue on S2 instead of S2.schedule on that line?
The question is, why does it continue on S2 instead of S2 schedule? Because we need an adapter. So S2 schedule produces a sender, but it doesn't take a sender. So now we need to adapt our sender chain, something that can take a sender, adapt it, and return a new sender, whatever that adaptation looks like. And in this case, continued on looks like adapting the sender that came in to now it's on a different execution context. This, by the way, what you just wanted to do for the first couple of weeks just killed me as I was working with senders. Luke's laughing in the front. I think Luke is still in that cycle of it.
Yep.
Yeah, Luke's still in the cycle of it. Like you just like, I've got this sender and I've got this sender, and I just kind of want to sequence the senders, right? So there's some internal discussion at the moment within our library. Do we just want to create a sequence when that happens?
Why do we have this 2 at all? So why can't we write just like then return 42 and assume then the next function goes out like
Yeah, why do we even have S2? Imagine, I don't know why, but imagine that this is that high priority interrupt that just went off. And then that high priority interrupt, it basically means, oh, I need 42 in the value channel. But I need to be done with the interrupt context because I need that interrupt context to be able to be used by something else. I don't want to actually convert my integer into a string in the interrupt. I want to do that somewhere else. This might be more complex work, right? So I'm saying, go do this somewhere else. Free that interrupt up again so it can be working again.
so but then functions they wouldn't execute asynchronously then?
They will not execute what?
Asynchronously?
Oh, they will not execute asynchronously. They're going to execute in order. At the moment, I've described a chain of events that will happen in order.
But they're sort of interruptible, right, with each other. So if we compose them.
So whether they're happening asynchronously or not, we want to get there, and we'll be in the depth of it here in a minute. Hold on to that question. John.
Is sync wait like a terminal, or can you continue after the sync wait? Like, is it just like another sender that you,
Can you start the sender again?
right, or can you put like sync wait and then put like your,
No, sync wait is a terminal. It doesn't return a sender.
okay.
Yeah, it only consumes. Dave?
When does this start?
What is the start?
When does it start?
When does it start? Within sync wait it starts. So our mental model is it starts in here somehow.
I think of sync wait as a packaging function. Like it makes us a receiver and it connects it and gets the operation state and then starts it. And it keeps that somewhere to the side so you don't have to worry about it.
Yeah, Gasper says it does a bunch of stuff under the hood that we don't want to talk about because we're users. And it makes the stuff run. We're going to move on just so I can get into the to some more stuff here. So here we are doing something similar to what we were doing before. On S1, we're going to schedule, this thing's going to happen on S1, whatever it is. Then we're going to say, send a get temperature to this device 1. On message, when I get a match on command equal 32, then I want to continue. Then take that message and do some stuff to it. Oh, well, this is just returning, it's grabbing the temp out of the message. Let value, we're taking and let value is going to expect that I return another sender. So it's the update temp sender. Delay 1 second, repeat this thing over and over again. I just want to start this detached, unstoppable. Just make the magic go off and do it. What is this doing? It's asking for the temperature. Sometime later, it gets a temperature. It then takes that, pulls the temperature out, tells it to the other thing that wants the temperature. This is our proxy problem. We brought the asynchronicity back to the state. By taking and having it all chained together, I don't have to think about this state problem that I had anymore. It's contained inside of the sender chain. So I don't have the problem that I had previously with our proxy. So we're going to be using this Intel bare metal sender library. If you want to ask lots of the under the hood questions, you want to know why we need a bare metal sender library as opposed to some other library. On Friday, Ben will be talking about all the gory details of what's under the hood to make the sender library work.
Question on the previous slide, if you want that. What's the reasoning behind putting async repeat as the inside the flow as opposed to giving it an unscheduled everything after a bar except for the schedule, as an argument?
Why did I put the repeat here as opposed to putting it down here?
No, I mean, the way I think of this is you have repeat. It takes a body, right? Because it's a loop. It's an asynchronous loop. The async sec and all of that stuff with delay, that's a body. I find it extremely weird to put it at the back.
Okay,
Inside the
don't worry. We have another slide where we won't do that.
All right.
Okay, so hello world in the little dev board market is blinking LEDs. You can blink LEDs for weeks and weeks and weeks and be incredibly happy. And your kids or your spouse will come in and they'll say, yeah, I saw it blink earlier. No, it's blinking differently. And then you start realizing you need to change the frequency of the blink so they actually realize it's either blinking at a different duty cycle or something, right? All right, so let's go ahead and, by the way, initialize board. You normally do the initialize board. Initialize board, that's the part that's really the hard part. We're not going to talk about it all. It takes you forever because you're like, I don't know anything about this device. All the bad stuff happens inside here. I didn't twiddle that bit on. I didn't turn this thing on. There was also a power bus that I didn't turn on. Are you kidding? You do not know how many days I just sat there knowing that there was some clock that wasn't turned on in this device. I just didn't know which clock it was. I was right, by the way. There was a clock, but like 5,000 pages of data manual, you got to figure out eventually which clock it was. So anyhow, we won't worry about initializing board. Here we go. We're going to set our LED to true. And then we're going to sleep. And then we're going to set it to false. And then we're going to sleep. And we're just going to loop over that over and over and over and over again. All right. What does our sleep look like? The best sleep in the whole world when you're first starting, you just burn energy. You loop. Is it sleep? No, it's like the opposite of sleep. It's like run around in circles real fast. That's okay. Yeah, okay, so we got to do a little bit of ugly stuff. We're going to do a lot of read, modify, writes because we've got these register things. They're just like it's magic hardware. And whatever the state is of the magic hardware, of the bits that we're not modifying, we need to keep them there. So we're going to read the magic state. We're going to modify the bits we care about, and then we're going to write what we want. Okay? So there's going to be a lot of this read, modify, write stuff going on. Everything is somewhere. It's like at some address. We're going to go ahead and we're going to, like this, it's the fourth bit of, this is not ODR. It does say ODR, but this is the output data register for GPIO port B. All right? Okay, good. So eventually, though, we just want to actually read, modify, write this address, that bit, that fourth bit, okay? Whether it's like we got the value or we don't have it, on or off. Bam, cool. All right, so we have a sleep heater, that's cool. Bit twiddling, not very composable. And like, we don't really ever really sleep. There's no real sleep. So let's see if we can introduce some senders into our Blinky here. Let's just start by composing things, all right? Sounds like a good start. So we're still going to initialize our board. We are going to start off with just, that has nothing in it. By the way, I've noticed this is code smell. I mean, I noticed it was code smell before Ben told me, that is code smell, buddy. But every time Ben sees this, I could see it. As soon as you saw this go up there, right? You were like, oh, there's a just that's not taking any parameters. You can kind of think of it as like, I got to get things going. I need a sender. I don't want it to do anything. I just need one because I need to chain some work to it. All right, so we're going to do that. Then we're going to set our LED to true. It looks exactly the same as what we had before, but now it's in a sender. And while true, blinky, sync wait. All right, I've done nothing, right? Except sorted some things around and composed them, and I have this lazy sender called blinky, and I can go ahead and sync wait it. And now my thing blinks, and my wife was still the same impression she was when the light was blinking the first time, which was not impressed, but whatever. Okay, let's see if we can go ahead and do some other things and break this up a little bit more, just so we can see how we can make compositions of senders. So within our library, we have async function composition because I complained about this all the time. I want to have just adapters that I compose into work units that do something, and then I can use them again later. Give them a name. I want to say that the on cycle looks like turning it on and then sleeping, and the off cycle looks turning it off and then sleeping, and then later I can just say on cycle, off cycle. Cool. I like composition. I like breaking things up and thinking about them in the smaller places. I like giving them names, and I like it if the code generates the same small code as it did before, which it does. So I'm happy. Composition's great. Yes?
In the while loop, do you create a new sender each time, or do you reuse the sender?
Oh, I'm reusing the same sender. So I've created one sender here, and in the while loop, the sender here basically has the instruction of what I want to do when I do it. And I do it when it actually meets a consumer. So it's meeting the consumer at this point, and so some action's going to occur.
So after sync wait at the end, right?
Yep.
But like you can restart.
Some of them you can restart, some of them you can't restart. Go to Ben's talk. We're going to just pass on that one for a moment. All right, so let's add a scheduler, though, because our while loop is just a while loop. So we have this fixed priority scheduler. It looks a lot like the thing that we had in previous pictures. In number of priorities, it works with this thing called a task manager. We need to define three things. We need to define a concurrency policy. Concurrency policies for our embedded thing just means, how do I guarantee I'm not going to stomp on something? What does it look like in order to say that I have like a critical section? We're going to put that in quotes, air quotes. Provide a method to signal that there is work to do, and we need to provide a mechanism to run priority items. So for critical section stuff, we're just going to create this disable interrupts lock. You're going to believe me at the moment that this does exactly what it's supposed to. I'll share the code later, you can see. And we check to see if the predicates have been satisfied. If they are, we go ahead and run whatever the function is. If not, we cycle back through the while loop, which releases the lock and then comes back and through. Very often what these look like, most often what they look like is shut all the interrupts off. Do something that needs to be atomic. Turn all the interrupts back on again. Do you want to do that for very long? No. You do not want to do that for very long. Okay? But we need some way in order to guarantee that our system is going to be consistent. And then there's a wonderful lightning talk about this, and I heard somebody just recently going, my mind was blown. Talk to Ben about this one too. It's how we do our injecting policies so that they can be used. Okay, notify that there's work to be done. So we need to provide some way to say that when there's work done, what do I do? It comes in with a priority. Schedule will get called with a priority. If it's priority 0, we're going to trigger interrupt 56. Why 56? Because I loved 56. It was the one that I wanted to use, okay? We're just going to trigger it in software that interrupt 56 has occurred. Cool. All right, we're going to create a priority task manager. It's going to use the interrupt scheduler. This is how it's going to figure out how to make schedule calls. How many slots does it have? 2, 0, and 1. It only has 2 priorities. And then I can inject that. All right, I'm done with that side. Now all I have to do is when I'm going to perform the work. How do I perform the work? On the interrupt service routine. Here's the interrupt service routine for 56. It happens to be DMA channel 2, or sorry, DMA 2 channel 1 handler, which I'm not using, so I don't care. So I'm just gonna like borrow the hardware's interrupt and use it for my own. What do? I simply call service task and give it which of the priorities I want to call. Bam, I'm done. I've now implemented everything I needed in order to get my tasks running. So now I can have my fixed priority scheduler, 0, schedule. So remember, this is actually going, and this is a factory. So we're creating our execution context, on cycle, off cycle. Blinky, I want to repeat Blinky. I want to start detached because I just want this to run forever. This is really, by the way, the very fun thing about my job is I only have to actually worry about startup code that gets static things initialized and constructed. I never have to destroy them. If our code stops, your CPU stops. It's awesome. It just runs forever. Okay, and then inside of our while loop here, I'm going to service task 1. All right, that's our main loop. Cool. So now I have my blinky light, totally still the same blinky light, burning a whole lot of energy still.
And it's undefined behavior.
I don't have any undefined behavior. It's perfect. Okay. Let's see what we can do about our sleep heater. So, we have a time scheduler. Awesome, time scheduler describes that I want to run a thing after a certain amount of time. So it's just like a scheduler, except that it's going to delay how long. So I can say time scheduler 10 milliseconds. This now is a scheduler that if I schedule work on it, I get an execution context, anything that gets scheduled on it will begin 10 milliseconds after it starts. How do I make one of these? I just need to teach it some things. First, I need to teach it something about time points. So I'm just going to use chrono. I'm going to say that there is a tick for every 16 megahertz. So I've got a tick for every 16 megahertz for this little board. Inject my timer task, or excuse me, define what a task looks like. Implement some things. I can enable it, disable it, set when the time needs to occur. I can ask, what is my time point now? And I'm done. Now I've implemented all the bits and pieces that are needed for a timer. Cool. Oh yeah, we have to teach it one more thing. We have to teach it how to go from time points to durations. Easy enough. Now we're done. So, set up the ISR for this. We're going to use timer 2. When its interrupt service routine goes off, I want to read, modify, write, and basically turn the bit off. I'm servicing the interrupt. Don't want it to be stuck in this. And then say service whatever the task is. Now I've plugged in the ability to use timers. So I can say continue on my timer scheduler 1 second, or continue on 300 milliseconds. So what did that do? Well, it transferred, continue on, it transferred to the execution context of this scheduler. It starts, what does it do? Nothing. Eventually the timer goes off, it then continues moving on. So now my Blinky doesn't use a whole bunch of power. It's still kind of icky, so let's see if we can make things a little bit nicer. Let's create this delay thing, and we can call it delay. And so we have on cycles and off cycles with 1 second or 300 millisecond delays. Now, great, except that, yes?
How did they get from the timer schedule back to the context?
It didn't.
Oh.
And so Richard is just tracking right here and realized this is not what I want, probably. My timer went off, and now I'm operating on the timer interrupt context to do all my work.
After that, yeah, you're always
Yeah, I'm always there. So once I got on the timer interrupt, now I'm operating on that execution context. But you want to know something? I love it. You know why I love this? All of the code is all locally right here. I don't have to wander across the code base to try to figure out which execution context are we running in at the moment and where is it. It's pretty easy to see that there's a bug. Richard found the bug. He's never seen these slides. Sebastian used to cheat. Okay, so we can create delay and transfer. Because I don't really want to just delay. I want to delay a certain amount of time, and then I want to transfer to an execution context. That's more likely what I want to do. So here we now have delay and transfer. What does it take? It takes what my time delay was. It takes where I want to continue on. And so now I can say that on cycle is going to be the LED on. Delay and transfer 1 second, transfer to scheduler 1. What's scheduler 1? My fixed priority schedule of 1. Okay? So again, now I've composed these together. I've got something that's very nice and easy to see what's going to happen. I don't have to trace all over the code base to try to figure out that, dude, I have inversion because this thing way over here in this other file just put all of my work on something that's running at the wrong priority. What a drag.
I'm probably missing something obvious, but why is delay and transfer a lambda instead of a function?
It could be a function because I wanted to write it as a lambda. And I'm just going to execute it right away so I could just put the code right here and it actually works. You can write a function. I might write a function too.
12 and 13 wouldn't compile it if that was a function.
That's right. Oh, 12 and 13.
Because it's a generic function. It's not a function.
It just needs to return a sender. Oh,
Yeah,
later.
but
I'm going to run out of
it's the
time.
object.
So I think it's quite common to continue on to the timer scheduler and then hop back to where I was.
Where you were before.
Is that a thing?
You know, we should talk later because I say that a lot also. I'm like, what I really want to be is where I was before, but I need to figure out how to forward that information across into the channel so that I can get it later. I say that to Ben a lot. And later, we can say it, you and I, to Kirk. Won't that be great? Kirk might even already have an answer. That's what I'm guessing. This is why I'm so excited about this. All right, so let's, I have only one more thing that I kind of want to solve in this. Well, actually, I have a lot more things, but let's talk about Groove real fast. So Groove, internally we use a library called Crew, just as interesting, that allows us to compose and figure out how to deal with registers and bit fields and say, like, I don't really want to deal with registers. This is where the field is. This is what its type is. I just want to write to it, or I just want to read from it. I just want it to compose at compile time the minimum operations to do what I want. If I'm writing to all of the fields inside of the register, I definitely don't need to read it first, right? Just write it. Like, this is the type of thing that Groove handles for us, but it's built with senders. because, as I mentioned previously, we have some problems. Our registers aren't always actually very local. Like, errors can happen. There's a reason that it didn't actually pass, and like, I didn't complete the register read, which you would normally think just can happen because I shut the fabric down or something else, right? Like, there's all kinds of things. You can think about, actually, there's a lot of things. I squared 2 looks like registers across the bus. Well, we could just use groove. It's all cinders. So normally you'd write junklet looks like this. It's beautiful. Let's not do that anymore. Instead, we write junklet looks like this instead. So inside of this register group, GPIOB, I have these registers and these fields, and I want to set them to actually real typed values so that they're correct and it will do the right thing. It will figure out when I go ahead and write it, it will figure out that how to optimize this, which registers it needs to go to, and how to make the minimum number of reads and writes. Okay, so now I actually can treat my register reads and writes as actual cinders. I can write now my LED writing like this. So I can either write this write method that takes the information, the register spec, whatever it's called. I just forgot the name, the path. Yeah, that thing. And then it goes ahead and just syncs weights. Or as you saw a moment ago, write can also be an adapter, so it will take whatever's in the stream and it can adapt. If we think about how would we write groove, what does it look like under the hood? And this is, to me, kind of the beauty of cinders and receivers. It's just using the primitives that we already had. And it now can be cinder available. How does it handle the, here we go. No, that's definitely not going to work. How do we handle piping? Piping's down here. It takes a cinder, and it's just going to use let value and whatever came in. Here we can see that when all of the operations for whatever the things are that we're writing to, excuse me, we're doing writes or reads? We're doing reads. When all the operations for all the reads are done for those registers, then do some other stuff. It's going to return some values. But as you can see, there's no other magic. It's just utilizing the cinder primitives that are already there to allow me to build up another cinder thing, which now has the capability of some of the registers can be remote, some of them can be local, some of them can be asynchronous. All right, so now we can just, we're completely cinderfied. All right, let's talk about logging real fast. Old style logging, and I want to, so this is very simple. We've got a UART. I just want to take whatever the characters are that came in, and I want to splat them out into some register by writing them here. I need to check until it's clear. I'm just using polling. Once it's clear, then I'm going to write the next register. When it's clear, I can write the next one. When it's clear, I can write the next one, all right? So just waiting for the parallel to get shifted out to serial. The register becomes available. I can write another one in. How would I do this inside of cinders? It's a lot more verbose. Is that good or bad? All right, so we're going to start off with, in this case, I'm going to utilize the iterator. I'm going to return whatever the iterator is pointing to into the value channel and increment it. Then, this then is going to return the new register spec of writing that value to the TDR register. It's going to write it, and then it's going to sequence, means I have another cinder I want to sequence in this operation. It doesn't care about any of the values coming in. Wait, so I need to still do that wait. What does the wait look like? It's going to read the value here. It's going to repeat until this bool goes to, it's going to repeat until it's clear. And then we're going to repeat all of this n times. What's n times? Whatever the sizes of the span that came in. And then sync wait. So now I've composed it together with cinders. Okay. So we can do this with interrupts. Interrupts, we can just create, it looks very much like the fixed scheduler, but now we can do this with interrupts. And now we can treat interrupts and say, I have an interrupt scheduler. When an interrupt occurs, do some things. Start and repeat it. I need to repeat that thing over again, right? I want to run that again later, start detached. So every time the interrupt occurs, this is the sender chain that I want it to run. Scheduler basically becomes this event handling building block. When I started working with senders, I was like, oh, well, that's what the context I want it to run in. Not very interesting to me. But at the end of the day, what a scheduler actually is the ability to respond to an event, any event. And so that could look like what we saw there. It could look like the messaging one that we saw earlier. What I said when I said basically on message. What is on message? On message is a scheduler. When this thing occurs, I want the next thing to happen. Events are handled by schedulers. It's the building block. All right, here's the summary of how this little thing works. So I have been, unfortunately, maybe only 2 months now playing with this library, dog feeding it. And in 6 months, I could tell you a whole lot more about how all this implementation went. But right now, what I could tell you is senders have solved the problems that I experience most in embedded systems, which is trying to figure out how do I keep events and state together with value channels? How do I respond properly to errors at all times? How do I cancel things when they need to be canceled? And how can I reason about my problem with locality instead of having things spread all over the place and trying to figure that out? I think it has a lot of promise. It has a lot of maybe work still to go, but it's really great. So continuation passing style, first off, is verbose. If you don't like verbosity, you're going to hear that complaint. You know, if you want to just like go through your little loop there, addressing the UART register and throwing things in it, you know, that's one way to do it. I wasn't going to use the M word, but I'm going to use it. Escaping out of it is hard. You want to stay in it as long as possible, right? That's the whole idea, is you want to stay inside of the continuation passing. You want to stay in the monad because it gives you the power of having the values or the errors or the stops when you need them. But when you get out of it, it takes a little bit of work to get out. Local reasoning, channels for values and errors, cancellation, it's part of the design. I think senders are awesome, actually. And I'm actually looking forward to it with inside of our own work, solving some real major hard to reason about problems that we have. Thank you. James.
This is a lot of fancy looking code on the slide. How does the code size compare to like whatever you would have done before?
Yeah, okay, so code size question. So we won't talk about compile times yet. Let's only talk about code size. So generally, the code size is pretty good. We have a few cases where it's large, but as Ben says, we haven't actually worked on that yet. Our expectation for this to work is it better be at least as good as hand-coded, if not optimized better. It's what we expect from like Crew and Groove. We expect register access to be as good as if we hand-coded it or better. And so our expectation is, and we don't have any reason at the moment to believe that the code generation won't be good.
If you go back a couple slides to the interrupt scheduler. Right here. I don't quite understand how the scheduler behaves. So if I just took that block of code, copy pasted it so it happens twice, what happens?
Oh, if you,
What is that start detached actually doing with the scheduler on which this gets?
yeah, so this interrupt scheduler only allows one thing. It would replace the other sender. Yeah, so at the moment, my implementation of the interrupt, this is my thing, not Ben's thing. See, Ben would have thought about it mathematically and gave you the proper operating thing. This is Michael's thing, which is you only have one interrupt service routine for an interrupt. If you have more, you better should do something else. So there's only one at a time.
I want to add something to that. Our other interrupt, like our actual schedulers.
Oh, the real ones.
Yeah, use intrusive linked lists. You have to be really careful with their allocation because everything is pretty much statically allocated.
He was asking about my little play library.
Yeah, I know.
We're much more sophisticated at work. Any other questions? Yes.
So one thing is like you said like this is great for error handling, but you never actually talked about.
Never talked about error handling. I only had 90 minutes.
Right. But like, do you have any like if this write fails, as you said, what happens with like the register rate?
For this, you would not, if this register rate fails, I'm in big trouble. Yeah, no. If something fails and I would hope then I would have had an on error, I would have like thought about my errors and did something about errors inside of my chain if I'm going to be detached. Right? Because you can think of it as, here's a chain of events that are going to occur. There's an error in that. I need to handle the error, and it needs to be described in the chain of processing that's going to occur in the sender chain because I'm going to start detached. Some people have really strong opinions about start detached, like, I mean, they haven't thrown up yet that I've noticed, but like they're really violently opposed to start detached. But in our world, everything is event driven. We have no context if there's no event, right? If there's not an event, we are not doing anything. So everything that we think about is detached, so to speak. It's interrupt driven or event driven somehow. And so we have a lot of detached. And we have the detached whether we want to write it or not. And if we write it this way and we have a sender chain that runs in the detached, then I can locally reason about what's going to happen.
So in the training process, at some point the cave jumped to the beginning or jumped to some specific point.
Oh, in the chain?
Let's say you have an error, you want to jump to the beginning. Is that possible?
You would, if you had an error and you wanted to jump,
Or some condition.
does repeat,
How long if you redirect the error to a value check?
you would, redirect the error to a value check, do something with it, and then you would be able to repeat back up. Yeah.
Since you're detaching this, do we need the timer interrupt variable? Is that doing anything?
Good question. Do you need the timer interrupt? Start detached. We have two versions of start detached. One that allows us to cancel, and one's unstoppable. So, or stoppable and unstoppable. So you get back the token that, or the thing that allows you to do that.
So this one is stoppable, which is why you have the variable so that you could cancel it if you want to.
Well, I have the variable there because it forces me to have the return value. It's a very nice little feature in the language that makes me get the return value, do something with it. I was waiting for a bit. It's no discard, yeah. It's there because it's no discard at the moment. But it might.
Unstoppable, then there wouldn't be a return.
I don't remember. Jeff. Oh, yes. Kirk. Ooh.
Going to the question of how you would jump back, repeat is a jump. It's just scoped to go back to the beginning. If you have retry, that would do it on an error. It would go back to the beginning. If you wanted to nest a block, say within a let value and retry there, you would be going to the beginning within the larger statement. So you can create smaller scopes where you are jumping to the beginning.
So I did that. I did that in this one here. Here's the wait TXE. It has a repeat until. It's all within this sender. This is a repeat in. It's repeating this sender context. So there's smaller repeats. David?
I just want to say thanks so much for this presentation. I feel like it's brought us to the point to where we can begin to have a meaningful design review of this thing. The question I have is how are compilations
I didn't understand that question. No, the question is how are compilation speeds? They're being worked on. Some things are great, and some things you add in and they're horrible. Kirk is going to.
For this, like what would it take? How many seconds would it take? Like roughly.
It would take. It's going to probably take about. I don't know that I've ever done this by itself, but like the little project that also controls some servos and does some other things takes about 30 seconds to compile. And it probably has a dozen sender chains. If you have a then in it, man, it compiles so fast. If you put in like a let in it, like there's a noticeable increase in second count, right? And there are certain constructs that definitely take more time. Kirk, did you want to respond to this?
So, compilation speed is a tooling problem, not a language problem, not a library problem. We are trying to hack around the tooling problems in the libraries. So, for instance, in the standard exec implementation that NVIDIA has built, Eric Niegler has created a means of erasing symbols from types by using lambdas so that the type is actually in the lambda and it replaces an entire huge type with a single lambda type.
Yeah.
The fact that we have to do these hacks is entirely a tooling problem. None of our tools deal with symbols appropriately. I mean, I've been dealing with this since like 2007, where I had a template-heavy library that generated 700 megabyte libs for a 1 megabyte binary. And it was entirely just in the fact that we are storing the same strings over and over and over and over again in the same symbol and across symbols, and we should not be doing that. It's a huge waste of resources.
All right, so let's talk about the sleep heater and the waste of resources over an espresso. Sound good? All right.